Hello, welcome to my talk all about the fluid. This talk is on Navier-Stokes equation. In this talk, I will show you how Navier-Stokes equation is derived using the transport theorem, and the focus will be paid on the understandings of the fluid shear stress and of the fundamentals behind the Navier-Stokes equation. In this slide, a very brief history of Navier-Stokes equation is presented. In 1757, Euler first derived the Euler equation, which unified the mechanics of fluids to a single point of theory, and laid the foundation for the establishment of the four fluid dynamic equation. The Euler equation is a universal equation for fluid dynamics with a drawback only for the inviscid flow. In 1822, Navier made the first successful attempt to use the concept of a pure molecular force to obtain the correct equation for the viscous flows. In 1827, Cauchy took the fluid as a perfectly inelastic body and first introduced the symmetrical stress tensor for fluids, which was based on his own symmetrical stress tensor developed for the elastic material, the solid. In 1829, Poiseuille took the fluids as a temporary solid and introduced the pressure into the Cauchy symmetrical stress tensor. In 1834, Saint-Valon used the approximation of molecules and slides for the four fluid dynamics equation. In 1845, Stokes studied the fluid friction on a pendulum and used a similar concept as that of Poiseuille to derive the four fluid dynamic equation in a very elegant manner. His method provided a standard derivation as we see in many textbooks today. In 1934, the four fluid dynamics equation was first named as Navier-Stokes equation by Prandtl when he gave lectures on the fundamentals of the hydro and the aero mechanics. To derive the Navier-Stokes equation, different methodologies can be used. In many textbooks, the derivations of the Navier-Stokes equation have been made using the fluid element method with the application of the substantial derivative and the Cauchy moment equation. Generally, the physics of this fluid element method is very clear and easy to understand. That's the main reasons why in many textbooks the fluid element method have been widely applied. However, it should be pointed out that in this method, the Cauchy moment equation must be used, while the substantial derivative cannot be applied on the Newton's second law of motion directly. If you are interested in the method, you can watch my talk on Euler equation. To provide more information on the derivation of Navier-Stokes equation in this talk, the method called the transport theorem is used. This method directly applies the transport theorem, i.e. the equation. Thus, the fluid dynamics equation can be easier to be derived. For this purpose, the transport theorem is first introduced here. The theorem calculates the differentiation for a volume integral of an arbitrary function in the fluid domain with regard to time. Here the capital V is for fluid volume, while the vector V is the fluid velocity with the arrow above the letter. It should be noted for the integral of the whole fluid volume, its normal derivative and its substantial derivative are same due to the fact that the integral on the entire volume would be the function of time only. Hence, in this talk, the normal derivative on the integral of the whole volume will be taken. In the derivation, the other important formula, Gauss divergence theorem, will be used. This theorem is the transform of surface integral of the entire fluid domain to the volume integral. Here, the capital T with double arrows means a tensor. Here, the continuity equation is derived first. For this purpose, the arbitrary function f can be simply taken as the fluid density. So, its integral on the whole fluid domain is actually the fluid total mass. Based on the mass conservation, it can be easily seen the differentiation with regard to time is 0. Now we apply the transport theorem. We can easily obtain the continuity equation in an integral form as this, and we can get this differential form for the continuity equation, this, and this is exactly the same as the continuity equation from the fluid element method. From this derivation, it can be seen the derivation from the transport theorem is much easier than the method of fluid element. For the moment equation, we can take the arbitrary function f as no v. So its integral of the fluid volume is the fluid momentum. Thus, we can apply the Newton's second law of motion for the fluid motion. The equation is given like this. Here, the body force and the surface force are included. The surface force is calculated from the total stress tensor. Now we use the Gauss divergence theorem. We can transfer this integral over the surface into the integral of the volume as this. Now apply the transport theorem. We can get this equation, the integral form of the moment equation. Its differential form of the moment equation is this. In the next few slides, I will make an explanation to the fluid stress tensor. Following Stokes' assumption, the total stress tensor is given by the tensor T. This total stress tensor contains basically three terms: the term from the pressure, the term for representing the fluid viscous stress, and the term for representing the fluid compressibility, where the lambda is the second viscosity coefficient. If we apply the index or the subscript 1, 2, 3 for representing x, y, and z, then the Cauchy stress tensor component are given by this. All these are symmetrical stress tensor. In many textbooks, we see a drawing like this. On the three specific plane on the cube, S1, S2, and S3, on each plane, there are three stress tensor components. For instance, on S1, we have tau 11, tau 21, and tau 31. It looks like all these stress tensor components have directions. So there will be a question: do the stress tensor components have directions? In this slide, the stress force is calculated on an average unit force. So stress force has three components, F1, F2, and F3. So the stress force calculated from the stress tensor tau. So we have this mathematical equation. If we draw this picture, we can see on the unit surface the stress force and the vector. So from this formula, we can see the individual stress tensor component has very weak link to the stress force component F1, F2, and F3. The stress force component are not only linked to the corresponding stress tensor component, but also to the normal vector component. For instance, F1 calculated from tau11, tau12, and tau13, and also it's calculated from the normal component N1, N2, and N3. To simplify the problem, special planes on a cube are used. The cube is aligned with the coordinates as seen in the figure. On these special planes S1, S2, and S3, all normal vectors have only one component, as we see here. So on S1 we have M1, on S2 we have M2, and on S3 we have N3. So on this specific planes, on S1 we have the stress force Fs1, and on S2 we have the stress force Fs2, and on 3 we have Fs3. So we draw all this stress force on the plane. We have a picture like this. Now specifically on S1, S2, and S3, the normal are all unit. Hence, the force on S1, S2, and S3 are simple. For instance, on S1, Fs1 has three components, tau11, tau21, and tau31. So this figure, if we apply the unit normal, we can get this drawing as we shown before. So only on this specific surface, we have very simple stress force. For instance, on S1, we have three components of the stress force, tau11, tau21, and tau31. In the next two slides, I will show you why the Cauchy symmetrical stress tensor is required. For a small cube, as shown in the figure, the stress tensor component, which could produce the moment in x direction, are only considered here, which are tau23, tau32, tau prime 23, tau prime 32. For a very small element, we can assume that the stress tensor component are constant. That is, tau 23 equals 2, tau prime 23, and the tau 32 equals 2, tau prime 32. These stresses could form the couples of the moment. For the first couple, the moment due to the stress tensor component tau 32 and tau prime 32 is in x direction. So delta mx1 is as this. And the moment due to the stress tensor component tau to 3 and tau prime to 3 is against x direction. So delta m x2 equals this. The total moment due to the stress tensor component is calculated as this. Because of the total moment acting on this element, it could induce a rotating motion around x. Its dynamic equation is given by this. Consider the moment of inertia of the element delta I xx. So we can calculate the rotation acceleration omega dot x given by this formula. Now we can look at this formula when the element becomes infinitesimal, i.e. delta y close to 0 and delta z close to 0. So the rotating acceleration of the element would become infinite unless tau 32 equals to tau 23. Similarly, we can prove tau 12 equals to tau 21 and tau 31 equals to tau 13. This proves for the force balance as required by the Cauchy's law of angular conservation, the stress tensor must be symmetric. This law was originally developed for elastic material, the solids, and then fully adopted to fluids by Cauchy in 1827, and it has been well accepted ever since. However, due to the difference between the solids and the fluids, a question should be asked: is this symmetrical stress tensor correct or required for fluids? Now we come back to the moment equation for fluid dynamics. To make the derivation easier, the moment equation can be written in Einstein summation as this, and the corresponding divergence of the second order tensor, we have this and this. However, if we look at the calculation of the divergence of a second order tensor, we may find a different formula for this, either this or this way. If the tensor is symmetric, both ways are correct. However, if the tensor is not symmetric, and these two calculations, this and this, will lead to different results. In this talk, all the tensors are symmetric, so we will use the first formulation to calculate the divergence of a tensor. So look at the total tensor as we talked before, and the Cauchy's symmetrical stress component. In a compact form, it's like this. So the tensor can be written in Einstein's summation. Hence, its divergence is calculated as this. Now we look at each term of this divergence of a tensor. The first term, due to the pressure, we can calculate it as this. And the second term, for representing the viscous stress tensor. So we have equation like this. And for the third term, this represents the fluid compressibility. If we look at the situation for the incompressible flow, the second term we can write as this. Consider this the continuity equation. The second term vanishes. So we have this, and Obviously, in incompressible flow, fluid compressibility is 0, so this term vanishes automatically. Now put all these terms together, we'll have the moment equation for the fluid dynamics, and apply the Stokes assumption. The second viscosity coefficient equals minus 2/3 mu, and then we have the final moment equation for the fluid dynamics. Now back to the form of vectors. The moment equation for the fluid dynamics is this. For the fluid dynamic equation, we have continuity equation as this, and the moment equation as this. The full fluid dynamic equation was later named as Navier-Stokes equation in 1934 by Planter when he gave lectures on the fundamentals of hydro and aero mechanics, and ever since the name has been used. So for incompressible flow, the fluid density is a constant. The incompressible flows have many practical applications. If the flow speed is not too large, for instance, if the flow speed is less than 0.3 Mach number, for air it would be about 100 meters per second. And in some cases, this maximum fluid velocity can be up to 0.5 Mach number. So for the air, it would be roughly 170 meters per second. As such, most of the practical applications can be considered incompressible. So the continuity equation can be simplified as this, and the moment equation like this. And from the moment equation, we can see clearly the substantial derivative for the fluid acceleration. If we write the fluid dynamic equation in detail, we have continuity equation as this, and the moment equation for the velocity component u, the component v, and the component w. In the next few slides, some examples will be presented for the exact solutions of the Navier-Stokes equation. The first example is the Hagen-Poiseuille flow. The flow is in a long horizontal circular pipe. The flow is under a pressure gradient delta P over delta X. Our target is to find the flow velocity distribution in the circular pipe. The problem analysis shows the velocity component v and w are 0. That means there's no flow in y and z directions. The velocity component u is the function of y only. Navier-Stokes equation is simplified as this. Apply the boundary condition, the no-slip condition, we can get the velocity distribution as this. Plot out the velocity distribution. We can see the velocity distribution is parabolic, with the maximum velocity at the center of the pipe and the zero velocity at the wall of the pipe. This example was very important since in 1800s many researchers have been working on deriving the full fluid dynamics equation. This included Navier-Stokes and in many others. The four-flow dynamic equation seemed settled of the Stokes because the equation was very successful in the application in the Hagen-Poiseuille flow, and it was validated with the experiment data. It was also this example, no slip boundary condition was formally accepted for viscous flow. The second example is the Couette flow. The flow is confined between two large parallel plates with a distance h. The bottom plate is fixed. The upper plate moves at a constant speed u0. The upper plate moving is very slow, hence the flow between the plates is steady and nominal. Our target is to find the flow velocity distribution. For the problem analysis, it is shown V and W are 0, and the U, again, is the function of Y only, and the pressure in this case is a constant. So Navier-Stokes equation is simplified as this. Apply the boundary condition at both plates. The velocity distribution is given by this equation, and drawing this, the velocity is linearly increasing with y. The third example is the Couette-Poiseuille flow. The flow is again confined between two large parallel plates with a distance h, and the bottom plate is fixed, and the upper plate moves at a constant speed u0. In this case, a pressure gradient around x is applied, delta p over delta x. We are going to use Navier-Stokes equation to find out the velocity distribution in this case. From the problem analysis, we can see the flow velocity component V and W are 0, and the U is the function of Y only. In this case, the Navier-Stokes equation can be simplified as this, and its solution is given by this after we apply the boundary conditions. It can be seen that Couette-Poiseuille flow is more complicated than the Couette flow. If we define the non-dimensional pressure gradient capital P as this, when the non-dimensional pressure gradient is positive, it means the pressure gradient delta P over delta X is negative. A higher pressure at the left-hand side and the lower pressure at the right-hand side. Hence, it is a normal pressure gradient. In such a case, the maximum flow velocity may be larger than the moving speed of the upper plate. If we see this picture, P2 and P3 here, so the maximum velocity is larger than moving velocity of the upper plate. When the non-dimensional pressure gradient P is negative, it means the pressure gradient delta P over delta X is positive, a higher pressure at the right-hand side. So this pressure gradient is a reverse pressure gradient. Under the reverse pressure gradient, the flow velocity may become negative, as we can see here for the case of non-dimensional pressure gradient equals to -2 or -3. In here, we examine the case for the non-dimensional pressure gradient P equals to -3. And we can see in this plot, there is a quite large portion of the backflow here. This is very similar to the flow separation near the surface. Hence, this example has a very good physical significance in understanding flow separation. From this example, it can be seen that the flow separation is caused by a relatively large reverse pressure gradient. This is actually true in practical application. The flow separation is caused by the reverse pressure gradient. But for the practical flow, especially the turbulent flow, the flow separation is much more complicated than this, which remains a challenge in flow dynamics.